Okay, so I want to go make one last video for the separation of variables stuff for this week, and then there's going to be, I uploaded some practice problems that I'll be posting to solutions to over separation of variables. But the last one that I want to go over is just going to be the wave equation. So the t derivative of u is equal, the double t derivative of u is equal to the double x derivative of u. We're going to look at the boundary conditions u of 0t equals u of pi t, and these are both equal to 0. And then because it's the wave equation, because it's the wave equation, we're going to need two initial conditions. U of x0 equals f of x, and the t derivative of u at x0 is equal to g of x. And I said because it's the wave equation, but the real reason is because we have a double t derivative here. And just like before, we're going to look for product solutions of the form. I'm going to call it uk of xt for now because we know, looking ahead, we're going to have a sum of them. uk of xt is going to be equal to hk of t times phi k of x. So we want to look separation of variables. Again, we're writing our solution as a product of two functions, and then we can separate variables. That's why it's called that. So if we take this, I'm just going to write h of t, phi of t for now, and we plug it into the PDE. On the left-hand side, we're going to get h double prime of t, phi of x, and on the right-hand side, we're going to get h of t, phi double prime of x. And if I rearrange, I get h double prime of t over h of t is equal to phi double prime of x over phi of x. Again, we have a function of t equaling a function of x, therefore they must be constant. And like before, we're going to write this as minus lambda. Minus lambda is that constant. Now if I look at my phi equation, just like before, I get phi double prime equals minus lambda phi. And I still have these Dirichlet boundary conditions. Phi of z equals 0, phi of 0 equals 0, and phi of pi equals 0. Well, we've done this before. We know that the eigenvalues are going to be lambda k equals k squared, and the corresponding eigenfunctions are going to be phi k of x equals sine kx. Maybe you want to put a constant bk there at this point. At some point you have to do it. For reasons that you will see, I'm not going to put the constant there. And this is for k equals 1, 2, and so on and so forth. Okay, so that's the phi equation. For the h equation, I have h double prime of t equals minus lambda h of t. Okay, well what's lambda? Lambda is minus k squared. So this is minus k squared. Well, that's just the same as this equation here, but I don't have any boundary conditions for h. All I can find is a general solution. I'm going to call this hk of t is equal to ak cosine kt plus bk sine kt. And that's why I didn't put the constant there. I'm putting it there and there. And so what we are concluding from the method of separation of variables is that u of xt, or what we want to do here, is say that u of xt is going to be equal to the sum k equals 1 to infinity times our hk of t, which is ak cosine kt plus bk sine kt, and then all of that in the brackets times sine of kx. And so what I want to do at this point is to compute what the ak and the bk coefficients are, and just like with the other equations, I'm going to use my initial conditions. And since I have an ak and bk sequence that I need to solve for, these two initial conditions is what's going to let me do that. So notice that in order to apply the initial condition here, I need to compute the derivative. So I'm going to do that here, compute the derivative, the t derivative of u. So this is going to be the sum k equals 1 to infinity. So it's just going to be the derivative of this part. That's a constant as far as t is concerned. So what we're going to get is minus k ak sine kt plus k bk cosine kt, going to be a little here, times sine kx, and I'll step out of the way. Okay, well, if I look at my initial condition on u of x 0, I'm going to have f of x equals u of x 0, and if I look at this and plug in t is equal to 0, well, notice those terms go away. Sine of k times 0, sine of 0 is 0, and cosine of 0 is 1. So this is just going to give me the sum k equals 1 to infinity ak sine of kx. Okay, well, I've done this problem before. I'm just writing f as its sine series, and we saw in previous classes or previous videos that, I don't know why I'm writing f of x here, I meant to write ak, that ak is equal to 2 over pi times the integral from 0 to pi f of y sine of ky dy. Okay, now if I look at my derivative here, g of x is equal to the t derivative of u evaluated at x 0. And what do we get here? Well, now it's this term that's going to be 0, because when you plug in t is equal to 0, you get 0. And this term is going to be 1. Or the cosine of kt term will be 1. Or the cosine of kt factor will be 1, leaving us just with k bk sine x. And so this is equal to the sum k equals 1 to infinity k bk sine kx. Okay, well, notice what's happening here. It's like we have k bk, and that's kind of like playing the k bk is kind of playing the role of the ak here. And so what this tells us then is kbk, kind of a fun thing to say, kbk is equal to 2 over pi times the integral from 0 to pi g of y times sine of ky dy. And if I solve this for bk, it's bk is equal to 2 over k pi times integral from 0 to pi g of y sine of ky dy. And that's it. So this is the solution. These are our formulas for AKs and BKs. In the practice problems, I've given a few examples where you have to actually solve the AK and BK. You're going to have to do that on the exam, solve for the AK and BK. And let me just say that on the exam, you're going to have to understand the separation of variables algorithm. In other words, if you see a problem like this, if you see, for example, this problem, and I give you what f of x is, and I give you what g of x is, it's perfectly fine, if you've been working on this a lot, to jump straight to this step right here, and say, this is what AK is, and this is what BK is, and then compute AK and BK. Doing things like that are perfectly fine. And if you've done a lot of these problems, you'll be able to do that. But on the other hand, you're also going to need to know how to go from this problem to this step and all of the things in between. So you're going to need to be able to do that. So I could give you, and probably will, give you a different PDE that you haven't seen before and ask you to either do all or part of this separation of variables algorithm. So I want you guys to keep that in mind as you're studying for the exam. And if you have questions about that, please email me, or even better, ask in the discussion forums.